Hello, everybody. My name is Masood Olia, and I'm back with another problem of the type that they're called statically indeterminate. So if you recall from other videos that I've made, that statically indeterminate basically is the type of problems where you have too many unknowns and not enough equations to solve the problem. So here in this problem, we have this horizontal beam, ABC, being subjected to this linearly increasing load in the shape of a triangle with a maximum intensity of 18 kilonewton per meter, and being supported with 3 wooden posts. So it says these wooden posts are made of wood, obviously, with a modulus of elasticity of 12 gigapascal. And they all have initial length of 1.4, and they have the same exact diameter of 120 millimeters. And what we want to determine are the reactions that are developed at these posts. Obviously, the beam is very rigid and initially in the horizontal position. So if you draw a free body diagram and we say, okay, this is the reaction developed at post A, similarly reaction at post B and post C. And if we, for the sake of finding these reactions and applying the equilibrium equations, if we change this distributed load to a concentrated load, clearly that would be the area of this load, which is half base of 3 meters times the intensity of 18, so that's 27. Where would we put that 27? Right through the centroid of this. And in fact, actually, to be exact, I have to put that right on at B. So that's 27 kilonewtons. Remember, the centroid of a triangle is a third from the right angle side, so a third of 3 meters would be 1. So it would be right at B. Why is this a statically indeterminate problem? Because as you could see, I have 3 unknowns, right? FA, FB, FC, and those are what we're trying to find, actually. And only 2 equations. We can balance forces in the Y. And I'm going to do that for you, right? I can say FA plus FB plus FC is equal to 27 kilonewtons, right? And then there's only one odd moment equation. And that's only 2 equations, but I have 3 unknowns. So that's why we have a statically indeterminate. We don't have enough equations. And I'll show you how we can handle, how we can overcome that. Okay, a good point to take moment, by the way, would be point B, because you see how that 27 and FB are there. And if we do that, we notice that F sub C times 1 meter minus F sub A times 2 meters is going to be equal to 0. And this is actually a very useful equation. It says F sub C must be equal to 2 F sub A. So here's one equation. Here's the equation that I got from balancing the loads, right? So I need one extra equation. And in this type of problems, the additional equation always comes from geometry. Geometry meaning, the deflection of this beam. And how would this beam logically deflect? So if initially this ABC was horizontal, and I'm kind of exaggerating here to show you what's going on, this guy will translate, and then because the most of the load is on the right-hand side, it will tilt more toward the right-hand side. So it would be something like this, combination of translation and rotation. So you see, this is point A, that's how much A is going to deflect. This is point B, that's how much B is going to deflect. And this is point C, and that's how much point C is going to deflect. Now we know that delta, the elastic deformation, is related to what? To this equation, F times L divided by EA, axially loaded members, right? So how could I establish a relation between delta A, delta B, and delta C, and then relate it to the force so I can get an additional equation? It's really simple. I'll show you how this is done. We need a pivot point. So if you make a triangle like this, so just concentrate on this green triangle. I'm going to redraw it here for you, actually. Okay. So notice that this is delta B minus delta A, isn't it? Because remember, this is delta B and this is delta A. And similarly, this piece is delta C minus delta A. So using a slope or similar triangles, then we can say, look, delta C minus delta A over 3 meters is the same as delta B minus delta A, right? Which is this guy divided by 2 meters. And what will happen then, we can establish an equation 2 times, and I will just cross multiply, right? Let's put it that way. And therefore, if you clean this up, we have 2 delta C minus 2 delta A. Bring everything to one side, minus 3 delta B plus 3 delta A equals 0. And then this equation eventually becomes, let's see, 2 delta C plus delta A minus 3 delta B equals 0. So how is this equation now is related to force? Because I need one additional equation related to force. And that equation, as I said, comes from here. So for example, delta A is what? FA times the length of A divided by EA. Remember, these posts are all made of what? The same material. They have the same area, the same modulus of elasticity, and the same length. So actually, if you replace these guys, like this guy with F sub C times L over EA, say similarly, F sub A L over EA, and 3 F sub B times L over EA equals 0, right? Notice that L over EA cancels, so we get an additional equation of, say, L is the same, E is the same, and A is the same. So actually, this pretty much is the force equation that I need. 2F sub C plus F sub A minus 3F sub B equals 0. So this is my missing third equation. Go ahead, solve the 3 equations. It should be very easy. Just instead of FC, put 2FA here. And instead of FC, put 2FA. And then you have 2 equations, 2 unknowns. Let me give you the answers. F sub A comes out to be about 5.79 kilonewton. Remember, F sub C is going to be twice as much. So that's going to be 11.57 roughly, well, I'm just approximating, 11.6 roughly. And then F sub B, it's going to be about 9.64. In fact, if you add these 3, the sum is going to be what? 27 kilonewton. So I just wanted to show you an example of a statically indeterminate problem. And as always, if you like the video, please subscribe, and I'll try to, on a weekly basis, come up with new problems. Again, thank you very much for watching and listening, and have a good day.